Dr. B. Govindaraj, Associate Professor and Head of the Department of Chemistry, Vijayanagar College, Hospital. I am dealing with Vijayanagar Sri Krishna Devaraya University, Ballari, B.Sc 6th Sem Chemistry Syllabus, Paper 6.2, Physical Chemistry part. Chapter is Electrochemistry. In electrochemistry, we are dealing with electrochemical cells. Whereas an electrochemical cell is defined as a system consisting of two metallic electrodes dipping into the same or different electrolytes, which are there in electrical communication. And these electrochemical cells are of two types. One is galvanic cell, another one is electrolytic cell. In this electrochemical cell chapter, we are dealing with in detail about the types of galvanic cells there. Whereas in case of electrolytic cells, and these electrolytic cells are the cells in which electrical energy is consumed to bring about a chemical change. Hence, in such cells, energy consuming electrochemical changes will take place. For example, electrolysis of an aqueous solution of HCl into hydrogen and chlorine. Whereas in case of galvanic cells, and these cells in which chemical energy is converted into electrical energy by virtue of any chemical or physical change within the cell. And in these galvanic cells, energy producing electrochemical changes will take place. Electrolytic cells are much used in metallurgical process of inorganic chemistry, where here in this physical chemistry part we are not dealing in detail about those things. We deal about these galvanic cells. We study in detail about these galvanic cells. These galvanic cells again can be categorized into chemical cells and concentration cells. Whereas chemical cells, wherein which electrical energy is produced due to chemical change occurring within the cell. Whereas in concentration cells, electrical energy is produced due to physical change takes place within the cell. And this involves a transfer of matter from one part of the cell to the other. That is concentration cell. Depending upon whether the two electrolytes are directly in contact with each other or not, in chemical cells, we have chemical cells without transport and chemical cells with transport. In chemical cells without transport, we use salt bridge, whereas in case of chemical cells with the transport, we don't have salt bridge. The two electrolytes are directly in contact with each other. Whereas in case of concentration cells, whether the difference of concentration is with respect to electrode or with respect to electrolyte, we have two types of concentration cells. First one, electrode concentration cell, other one, electrolyte concentration cells. In case of electrode concentration cells, depending upon the nature of the electrode, we are going to use it there. We have again two types of electrode concentration cells. One is amalgam concentration cells, another one is gas concentration cells. Amalgam concentration cells are constructed only for those metals which are highly reactive with its own ions or with the solution itself there. Just like alkali metals like sodium, potassium, which are violently and vigorously reacting with water, we can't use a metal ion electrode by using sodium, potassium like that. So instead, we go for the respective amalgams there. So in case of amalgam concentration cells, the two electrodes belongs to the same material. Suppose it is sodium amalgam, we have sodium amalgam at anode and sodium amalgam at the cathode also. Electrolyte is also same. But the concentration of sodium in anode amalgam and concentration of sodium in cathode amalgam will be different. For example, at anode we can have 12.5% of sodium amalgam, and at cathode we can have 25% of sodium amalgam. So the concentration difference is only with respect to the electrode. That's why this type of cells are called as amalgam electrode concentration cells. Like that, if the electrode material is a gas, we are using gases for constructing electrodes also. Such type of cells are called as gas electrode concentration cells, where anode and cathode will have the same gas and electrolytes will also be the same, but the gas concentration, electrode concentration will be different. For example, if you are using hydrogen electrode, hydrogen gas at anode as well as hydrogen gas at cathode. Electrolyte is HCl, in cathode also it is HCl. So same materials are there, but at anode hydrogen gas is maintained at 1 atmospheric pressure, whereas at cathode it is maintained at 5 atmospheric pressure. So there will be difference in the concentration of gas there. That's why these electrodes are called as gas electrode concentration cells. Like that, if the concentration difference is with respect to the electrolyte, and those concentration cells are called as electrolyte concentration cells. Here in this case, we have the electrode material is same, electrolyte is also same, but the concentration of the electrolyte is different. Because of the difference in the concentration of the electrolyte, the potential is being developed here. That's how these cells are called as electrolyte concentration cells. And again, in these electrolyte concentration cells, whether the two electrolytes are directly in contact with each other or not, depending upon that, we have two types of electrolyte concentration cells, that is concentration cells without transport and concentration cells with transport. In case of concentration cells without transport, we have a salt bridge there is no liquid junction potential. Whereas in case of concentration cells with transport, here the two electrolytes are directly in contact with each other. That's why there develops a liquid junction potential. So the measured potential includes the potential in accordance with the oxidation and reduction plus the potential developed at the liquid junction. So liquid junction potential exists in case of concentration cells with transport, and liquid junction potential will not arise in case of concentration cells without transport. So these are the things we are going to study in detail in this electrochemical cells chapter. And these are the learning objectives for the students while studying this chapter in detail. The types of electrochemical cells, identifying the main components of an electrochemical cell, writing the electrode representation of an electrode and a cell representation of an electrochemical cell, and description of a Daniell cell, a label diagram we are going to study in detail, and working of Daniell cell, and writing down the electrode reactions at anode and cathode, and writing down the cell reaction also, and calculating the cell voltage using standard reduction potentials. And the next part we are studying the types of reference electrodes. So as we discussed earlier, we have two types of electrochemical cells, electrolytic cells and galvanic cells. So electrolytic cells, wherein which electrical energy is converted into chemical energy and electrical energy is used up to perform chemical reaction. Whereas in case of galvanic cells, chemical energy is converted into electrical energy and electrical energy is produced by performing chemical reaction. In case of galvanic cells, energy is out, that means energy has been produced. Whereas in case of electrolytic cell, energy has been utilized, electricity has been utilized here. On that basis, we can say that in galvanic cell, energy is out, whereas in case of electrolytic cell, energy is in. And in these electrochemical cells there, again we can categorize into two types of galvanic cells. One is reversible cell, another one is irreversible cell. An electrochemical cell can be a reversible cell if it satisfies the following conditions. If an EMF exactly equal to that of a cell is applied from an external source, the chemical reaction takes place in the cell will stop, that is no current. So here in this case, in the diagram we can represent at the first part, we see that the cell EMF E1 is exactly equal to the opposing EMF E2. In such case, no current will flow. The second condition is if the external EMF slightly greater than the actual EMF of the cell is applied to it, the current will begin to flow in the opposite direction and the cell reaction gets reversed. That is, you can refer to the diagram 3 there, where the applied EMF is more than the cell EMF. In such case, the direction of the cell reaction will be reversal. The third condition is if the external EMF slightly lower than the actual EMF of the cell is applied to it, and a very small amount of current will flow corresponding to very small amount of chemical change taking place in the cell. So that's how the diagram 2 we can observe it here, where E1 is greater than E2. There we are observing that the cell reaction going in the cell reaction in a very slow manner. Whereas, for example, for this reversible cell, we can take an example of Daniell cell there, where zinc is placed in zinc sulfate and copper is placed in copper sulfate, wherein which we are observing that zinc undergoes oxidation and copper ions undergo reduction, and we can get the reaction as zinc plus copper plus 2 giving rise to Zn plus 2 plus copper solid. So this reaction will take place. And whereas if the external EMF is slightly greater than the actual EMF of the cell is applied to it, the current will begin to flow in the opposite direction and the cell reaction will get reversed, as we see that here copper plus Zn2 plus giving rise to copper plus 2 plus Zn there. That is the reverse reaction of the earlier one. Such type of cells are called as reversible cell, and here in this case Daniell cell is a reversible cell. We can consider another example of irreversible cell, wherein which we are observing that zinc is placed in sulfuric acid and we get zinc sulfate and hydrogen. So zinc is oxidized to zinc plus 2 ions and H plus ions are reduced to hydrogen gas. In other words, zinc dissolves at one electrode and hydrogen gas is evolved at the other. If the cell is connected to an external source of EMF whose EMF is slightly greater than that of the cell and it is opposing the cell, then the silver dissolves at one electrode and hydrogen gas is evolved at the other. So you can observe that 2Az plus sulfuric acid giving rise to Az2SO4 plus hydrogen. And we can observe it here. Now oxidation takes place at the silver electrode and reduction at the other. Thus the condition is reversibly is not satisfied, or the chemical change is not a reversible reaction. That's how Zn plus 2H plus giving rise to Zn2 plus H2 is not becoming a reversible reaction, just like Zn2 plus H2 giving rise to Zn plus 2H plus. Instead, a new chemical reaction takes place. Hence, the above cell is not categorized as a reversible cell, but it is called as an irreversible cell. That's how we can make a difference between reversible and irreversible cells. This is a typical Daniell cell. We can have the Daniell cell construction here by taking two electrodes, zinc electrode and copper electrode. Zinc electrode is left hand side electrode where oxidation takes place, which is called as an anode, and copper electrode is placed at right hand side of the cell and where reduction takes place, and it is placed at cathode. So anode is zinc electrode and cathode is copper electrode. We are observing it here. Zinc is placed in zinc sulfate solution. That's why zinc undergoes oxidation giving rise to Zn, giving rise to Zn2 plus 2 electrons, where electrons have been released. At the right hand side electrode, we are observing that copper placed in copper sulfate, where copper plus 2 ions will receive those 2 electrons and copper 2 plus ions will be converted into copper atoms and they will be deposited on the copper plate. So to make an electrical contact between these two electrodes, we use a metallic wire, so that in between we are connecting it to the voltmeter, so that potential can be directly measured by means of a potentiometer there. And to make an electrical contact between these two electrolytes at anode and cathode, that is zinc sulfate and copper sulfate, we use a salt bridge. Salt bridge is an inverted U-shaped glass tube. At the lower ends it has been kept with cotton plugs there. The solution has been filled with a KCl solution, uni-equivalent electrolyte like K plus and Cl minus, so that there will be a contact between these two electrolytes indirectly by using salt bridge there. So in this Daniell cell, we are observing that zinc electrode, anode, copper electrode, cathode. Always at anode oxidation takes place and always at cathode reduction will take place. Therefore, always electrons are released at the left hand side and they are being received at the right hand side electrode. This is a typical Daniell cell, and these two electrodes have been connected to a potentiometer for measuring the EMF of the cell. Anode reaction appears leftmost while cathode reaction appears rightmost. All redox forms of reagents present should be listed, phase and concentration specified in bracket. That is zinc sulfate in bracket aqua, and that is 1 molar solution. A single vertical line is used to indicate a change of phase, and a double vertical line indicates a salt bridge. A comma should be used to separate two components in the same phase. Each metal in touch with a solution of its own ions. External circuit carries electrons transferring during the redox process. A salt bridge containing neutral ions completes the internal circuit. With no current flowing, a potential develops, the potential for work. Unlike the reaction in the beaker, the energy released by the reaction in the cell can perform useful work like lighting a bulb. That means instead of an voltmeter, if you place a bulb there, when electricity flows, electrons are released at anode and electrons are accepted at cathode, and because of this movement of electrons and electricity is passing through that, and because of that, bulb will start glowing. That is also indicating that electricity is producing it here. And labeling the parts of this Daniell cell, as we discussed earlier, at the LHS anode will be there, at the RHS cathode will be there. Anode is zinc electrode and cathode is copper electrode, and we have zinc sulfate at anode and copper sulfate at cathode as electrolytes. To make an electrical contact between these two electrolytes there, we are using a porous barrier or a salt bridge, and we are observing it here because of this movement of these charged particles. We are observing that anions are moving from right to left and cations are moving from left to right. Here zinc displaces copper from copper sulfate. In direct contact, the enthalpy of reaction is dispersed as heat and no useful work is done. For redox process, zinc is the reducing agent and copper plus 2 is the oxidizing agent. So zinc gives rise to Zn2 plus aqua plus 2 electrons, whereas at the cathode, copper 2 plus aqua plus 2 electrons giving rise to copper solid. So in a galvanic cell, at cathode, that is where reduction occurs and there where electrons are consumed and where positive ions are migrate to and has a positive sign. Whereas in case of anode, where oxidation occurs, where electrons are generated, where negative ions are migrated to and has a negative sign. Cell notation. Anode is on left, cathode is on right. Electrons flow from left to right. Oxidation on left and reduction on right. Single vertical line always represents electrode bar electrolyte boundary, whereas double vertical represent salt bridge. That's how Daniell cell can be represented as Zn solid bar, Zn2 plus aqua double bar, copper plus 2 aqua bar copper solid. That's how cathode representing at RHS and anode representing at LHS. And the connections here, the cell potentials and the free energy. The cell in open circuit generates an electromotive force or potential or voltage, and this is the potential to perform work. Energy is charge moving under applied voltage. Therefore, energy is equals to charge into voltage. That means 1 joule is equals to 1 coulomb of electricity and 1 volt of potential. Relating the free energy and cell potential, the Faraday value F is equals to 96,485 coulombs per mole, and delta G, change in free energy, is equals to minus NF into E, where delta G is change in free energy, N is number of electrons exchanged, F is Faraday electricity, and E is potential developed. At standard conditions, that means the concentration of electrolyte is 1 molar. If it is gases, their concentrations are represented in terms of their pressures, that is 1 atmosphere, and temperature is 25 degrees centigrade. Therefore, for standard conditions, you can write the same reaction as delta G0 is equals to minus NF into E0. Standard reduction potentials. The total cell potential is the sum of the potentials for the two half reactions at each electrode. That means EMF of the cell is equals to EMF of the cathode plus EMF at the anode. That means electrode potential developed at cathode and electrode potential developed at anode. So from the cell voltage, you cannot determine the values of either cathode or anode. We must know one of them to get the other one. Enter the standard hydrogen electrode, that is SHE, and all potentials are referred to SHE as zero voltage. So zinc half cell with standard hydrogen electrode, when it is connected to standard hydrogen electrode, cell measures a potential of 0.76 volts. Where a standard potential for zinc is equals to Zn2 plus aqua plus 2 electron, that is oxidation it is representing, therefore it is 0.76 volts. So this is oxidation potential of zinc electrode. But according to IUPAC convention, always we have to represent it in terms of their respective reduction electrode potential. Therefore, reduction electrode potential of zinc electrode here in this case is minus 0.76 volts. Like that, when there is no standard hydrogen electrode is there, in this cell there is no standard hydrogen electrode and the measured voltage is 1.10 volts, because at zinc electrode we have 0.76 volt of oxidation potential, and at cathode copper electrode will have 0.34 volts of potential, reduction potential. And when they are represented as oxidation potential and represented as reduction potential with respect to zinc and copper electrodes, it is 0.76 volts for zinc electrode and 0.34 volts for copper electrode. And the standard reduction potentials, any half reaction can be written in two ways: oxidation, liberation of electrons, whereas reduction, it is accepting the electrons. Their listed potentials are standard reduction potentials. Standard reduction potential, the cell potential, you can write it as for the Daniell cell as 1.10 volts at 25 degrees centigrade. That means oxidation potential at zinc and reduction potential at copper. 0.76 plus 0.34 is equals to 1.1 volts. Or when they are both are represented in terms of reduction electrode potentials, cell potential is equals to EMF at the cathode minus EMF of the anode. That means they are both are representing in terms of reduction electrode potentials. In such cases, EC is 0.34 volts in terms of reduction electrode potential, and EA is minus 0.76 volts in terms of reduction electrode potentials. Therefore, EMF of the cell is equals to EC minus EA, that is 0.34 minus of minus 0.76, that becomes 0.34, minus of minus is plus 0.76, and we'll get it is 1.1 volts. That is called as standard cell potential, and we can represent it as E0. And E0 is the quantitative measure of the tendency of reactants to proceed to products when all are there in their standard states at 25 degrees centigrade. So depending upon their electrode potentials, whether they are more prone for oxidation or they are more prone for reduction here, this table we consider as electrochemical series, where we are having hydrogen at the center, which is arbitrarily given with zero potential, and the electrodes which are placed above the hydrogen, so they are more prone for reduction, whereas the electrodes which are placed below the hydrogen, they are more prone for oxidation. That's how we are observing that here the standard reduction potential for these metal ions will be in the decreasing order of their reduction electrode potentials, and this list we call it as electrochemical series.